So exploring collisions in one dimension, we're only going to imagine now cars colliding or trucks colliding in the x direction, or balls colliding in the x direction, or boxes, or whatever, what have you. But we're only going to worry about one-dimensional collisions for the time being. And we're going to also restrict our analysis to elastic collisions in one dimension. Now, an elastic collision is a special type of collision, in that an elastic collision is one that conserves kinetic energy. So the total kinetic energy of the system before the collision, if you add up all the kinetic energies of all the objects in the system, that total kinetic energy before the collision is equal to the same total kinetic energy after the collision. Now, the individual objects in the system may have different kinetic energies before and after, but the total sum of the kinetic energy is the same. This actually defines what an elastic collision is. So, elastic collisions tend not to lose kinetic energy, or they don't lose kinetic energy, as opposed to inelastic collisions, which do, and we'll talk about those in a moment. So, elastic collisions, if your book says it's an elastic collision, you can actually also use the conservation of kinetic energy when solving the problem. All collisions conserve momentum, so it doesn't matter what type of collision it is. If it's an elastic or inelastic collision, momentum is conserved. So, internal kinetic energy we're just going to define as the total kinetic energy of all the objects in the system. You add them up before and after the collision. If the collision is elastic, those values will be the same. If it's inelastic, the final kinetic energy will be less than the initial, right? Energy is lost. Well, where does the energy go in an inelastic collision? We'll talk about that a little bit later, but it goes mainly into deforming the object. So, initial kinetic energy is equal to final kinetic energy, total kinetic energy for the system. Or in the case of two objects colliding in one dimension, 1/2 the initial mass, the mass of object 1 times the initial velocity of object 1 squared, plus 1/2 the mass of object 2 times the initial velocity of object 2 squared. That's the total initial kinetic energy, is equal to 1/2 the mass of object 1 times the final speed of object 1 squared, plus 1/2 the mass of object 2 times the final speed of object 2 squared. So here's the initial kinetic energy of object 1, initial kinetic energy of object 2, final kinetic energy of object 1, final kinetic energy of object 2. Kinetic energy is a scalar, so it doesn't actually even matter if it's a one-dimensional problem. There is no direction associated with kinetic energy. Now again, this equation can be used for collisions only if those collisions are elastic. If the collisions are inelastic, kinetic energy is not conserved. Momentum still is. So again, looking at the homework problems and the example problems I've posted, look at examples of how to solve elastic collisions. So you have two sets of equations. You have this conservation of kinetic energy equation, and you have the earlier conservation of momentum equation for two objects that we looked at in the previous video. So you have two sets of equations to solve these problems. And if you remember your algebra, if you have two sets of equations, then you can solve for two unknowns. There are four unknowns here, right? We don't know what the mass is of object 1, perhaps. We don't know what the mass is of object 2 is. We don't know what the initial velocity of object 1. We don't know the initial velocity of object 2. That's just four unknowns in the beginning. And then there are two additional unknowns at the end, the final velocities of object 1 and 2. So that's a total of 6 unknowns in that equation. I have to give you at least 4 of those so you can solve for the other 2 using this equation and using the equation for conservation of momentum. Usually what you solve for is you're given the initial status of the system, and you want to find out what the final velocity is of object 1 and the final velocity of object 2. If you have those 2 as unknowns, in an elastic collision you can solve for those final velocities.